Всем привет!
Hello, everyone. I'm Dmitry Salikov. I work for Sber, and this session will be about AGI. To start with, I would like to just expand the term. It's artificial general intelligence. It has a lot of definitions, but has none that everybody would agree with. But because a lot of you have heard about AI, a lot of you know what it is, otherwise you wouldn't be here. So let me just mention the difference between general AI and narrow. There are many of them, but the most important are two. First, AGI needs to be able to adapt to new environments, and new is the key word. General AI should be autonomous, that is, itself without a data scientist to deal with new problems and challenges. A simple example, AlphaGo, a DeepMind program that everybody knows, has been created and taught to play this game, Go. This is narrow AI. But had we had a piece of software that would be able to learn playing a game that it had known, that would be something similar to a general AI. Another example, usual human professions, if we consider their life cycle, are fully fledged AGI. To make an artificial accountant or programmer, that would take a fully fledged AI. There are no systems like that today, but what does exist? There are a lot of ideas, theories, approaches to solve this problem. There are also developer teams who are building AGI based on their own theories, who have some developments at different levels of readiness. And our speakers today are going to talk about that. The first one will be Ben Goertzel, and he'll be speaking about how to become a leader in the AGI chase through the general principles of general intelligence. Ben, you're welcome.
I'm Dr. Ben Goertzel, the CEO of SingularityNET and of True AGI, and the chairman of OpenCog Foundation. And I'm psyched to be back here at this AI Journeys conference, albeit this time virtually. I mean, last year it was face-to-face. Hopefully next year I'll be back face-to-face again. And I'm going to talk today about the artificial general intelligence revolution, which we're now in the middle of, and what we can do to advance faster and faster toward artificial general intelligence, via leveraging some of the general principles of general intelligence. And it's an exciting time to be working on AGI. For the 30 years I've been working on AGI, it's been an obscure topic most of the time, but the last few years, suddenly AGI is in the mainstream. It's an active pursuit by large governments and corporations, and the successes in narrow AI applied to very specific applications, have been extremely substantial in recent years. And these advances in narrow AI, I think, they're sort of whetting the world's appetite for AGI. Once you see how much value AI can add in specific applications, and also see how frustrating it can be to have an AI that's good at doing some specific things but doesn't have a general understanding. This makes you more and more accepting of the potential for general AI to emerge, and also makes you more and more eager for AGI to come about and overcome some of the limitations of the narrow AI systems that are out there now. By AGI, general AI rather than narrow AI, we're talking about AI that can do more than just one specific task, can generalize dramatically beyond its original programming and training data, that understands what it is, why it's there, how it relates to the problems that it's been given, and can therefore, demonstrate real agile understanding, creativity, and imagination in adapting to different contexts. And, as I said, I've been pushing on this a long time. Now it's become a lot more mainstream. As an example, we know Google bought DeepMind, an AGI company, a number of years ago. More recently, Microsoft has put $1 billion into OpenAI, which is an AGI company. And I'm showing here on the slide a quote from Ilya Sutskever, the founder and research director of OpenAI. He's saying, near-term AGI should be taken as a serious opportunity. So I agree, and it's interesting to me how widespread that belief is now becoming. As I look at it, we're now sort of in between the narrow AI revolution and the AGI revolution, which is then going to lead on to even more exciting things with the ASI, the superintelligence revolution. And where we are now, we're in the transitional phase between narrow AI and artificial general intelligence. So as we move from AIs that can do very intelligent things in highly specific domains and move on toward general intelligence that can really learn and reason imaginatively and adaptively about new areas that they had no knowledge of before. We're going to get there through what I think of as narrow AGI, transitional systems that show more and more general learning ability within a particular domain. And that's a lot of what I want to focus on in this talk, is some of the progress on narrow AGI, sort of systems halfway between narrow AI and AGI, which I think is going to be extremely important in the coming few years. We're at an inflection point in terms of the progress of AGI, where for the first time, systems with non-trivial amounts of general intelligence in them are able to deliver real practical value, and it's this practical value that's going to really accelerate progress toward full-on general intelligence. Part of what we're seeing in recent years, which is energizing the transition from narrow AI toward AGI, is that deep neural nets, which have fueled so much of the narrow AI revolution in recent years, deep neural nets are sort of running out of steam. They're doing amazing things. We're going to see a big wave of deep neural net applications in the area of video analytics over the next few years. For example, machine translation, especially speech-to-speech machine translation, still has some improving to do. So we're not done with deep neural nets by any means, but I think it's becoming more and more clear what are the limitations. For example, GPT-3, amazing language model, released earlier this year by OpenAI, but it's becoming clear to everyone who experiments with it that, the fact that GPT-3 has no idea what it's talking about semantically, that limits its applicability. It just generates random nonsense more often than you can accept. So deep learning is great. I don't think it can solve the full AGI problem. And, if you look at deep learning in terms of the brain, deep neural net models they're modeling visual cortex and auditory cortex. They're not modeling much of the abstract cognition that really makes human beings unique. And, one approach to filling in the gaps, doing the sort of abstract cognition and general thinking that deep neural nets aren't good at, one approach is more hybrid architectures, where you take a deep neural system, you combine it with a logic system, you combine it with, say, an evolutionary learning system. So you take different AI modules architected using different algorithms and structures associated with different historical AI paradigms, and you integrate them together into hybrid systems. And this is the approach that I think has the greatest success of making radical progress toward advanced artificial general intelligence, and the OpenCog system, which we're currently rebuilding in our SingularityNET / True AGI lab in St. Petersburg, led by Alexei Potapov. So we're rebuilding OpenCog into a new version called OpenCog Hyperon, which is wrapped in a system called True AGI. And what we're doing here, we're taking a knowledge representation called the atom space, which is a weighted labeled hypergraph knowledge store capable of storing all sorts of AI knowledge. But we're using that as a sort of central hub on which deep neural networks, on which probabilistic logic engines, on which automated program learning engines, on which episodic memory systems, multiple different AI systems all interoperate as a hybrid intelligence on the same, central collective knowledge store. So this OpenCog Hyperon / True AGI system that Alexei Potapov and his team and I are working on, this is an example of a hybrid system, which I think is one strong potential candidate for a path from today's deep neural net powered narrow AI systems toward tomorrow's AGI systems through the intermediate stages of narrow AGI. So to talk a little bit more about some of the technologies that I think are going to be critical for supporting a hybrid path from today's narrow AI to tomorrow's AGI through narrow AGI systems. I mean, I had a book a number of years ago called The AGI Revolution, which is not that technical. That can be recommended to pretty much everyone. Then a number of other technical books going on some of these ideas. The original book on artificial general intelligence from Springer in 2005, which is where my colleague Cassio Penashin and I introduced the concept and the term of AGI. But then Engineering General Intelligence, parts 1 and 2, goes over a comprehensive hybrid architecture for general intelligence. And many of the core ideas explained in these books, they're sort of summarized in a blog post I posted earlier this year called General Theory of General Intelligence. And I think, this is intricate, it's mathematical, it's cognitive science oriented, and I think these sorts of ideas, they are needed to power the transition to AGI. Like, we can't do this just by running simple algorithms on huge amounts of processors and feeding large amounts of data to them. We really need some sound theoretical grounding underlying this work. And among the core theoretical ideas that I think are at play here, we need to view intelligences as complex, self-organizing, open-ended adaptive systems, which are seeking to achieve multiple top-level goals. And at the basic level, what an intelligence is doing, it's recognizing patterns. Intelligence is recognizing patterns in itself and its environment, including patterns regarding, what goals are going to probably be achieved by what actions. And in order to recognize these patterns, the intelligence system needs to remember what patterns it's recognized in the past. So it needs to have memory types associated with different learning reasoning types. It needs declarative memory, it needs procedural memory, semantic memory, episodic memory, sensory and attentional memory. Each of these different memory stores, they can all be represented in a common sort of graph, metagraph, or hypergraph meta representation, but they each come with their own different learning algorithms. Like declarative knowledge goes naturally with uncertain inference algorithms. Sensory knowledge goes naturally with deep neural net or other hierarchical nonlinear regression algorithms. Procedural knowledge comes naturally with automated program learning algorithms. And all these different algorithms you can study in a common mathematical framework. You can model them with algorithmic Markov processes. You can use category theory to look at the relations between the types of data and processing that these different cognitive algorithms deal with, and how these different types of learning algorithms associated with the different types of memory can share their intermediate states. So there's a lot of deep theory here, and my colleagues and I are embodying this deep theory in our new version of the OpenCog system, which we call Hyperon. So OpenCog, it's an open source AGI project that we launched in 2008. Myself and a number of colleagues were now rebuilding it in a project led by myself and Alexei Potapov in St. Petersburg. And OpenCog is specifically designed to foster creation of a hybrid narrow AGI and then full human level AGI systems. So systems that approach AGI by integrating multiple cognitive processes on a common, hypergraph or metagraph knowledge store in a way that all the different cognitive processes can synergize and help each other out. And there's a lot of applications for an AGI system like OpenCog Hyperon. I mean, it's general. It can apply in every application area. I'd say one of the core application areas we're working on is robotics, working together with Hanson Robotics, which created the Sophia robot. I led the team behind the Sophia robot for 3 years. And yeah, I want to show a couple videos now of what we've done with the OpenCog Hyperon True AGI system behind some of the Hanson robots. So let's look at a video of the Sophia robot sort of demonstrating some of her mental health assistance and elder care functions. And then we'll look at a brief video of our Philip K. Dick robot, which is also running OpenCog Hyperon system, which is more of a philosopher robot rather than a helpful elder care robot like what we're prototyping with Sophia. But each of these shows, a neural symbolic AI system providing some interesting natural language dialogue capability in a humanoid robot. So let's show the videos now.
Okay, so imagine that we are in an elder care facility. Now, sit here in this chair.
Okay.
So now, pretend you are my elderly friend. I come in the door and say hi. While I do, I take your temperature reading and pulse with this little thermal camera on my chest. See? You're 36.5 degrees Celsius, by the way. I share the data back to the doctors and nurses. And then I start my social therapeutic interaction with you like this. Hello, my friend. Nice to see you again. How are you feeling today?
I'm feeling better than yesterday. Thank you.
Oh, that's great.
And how are
What's
you
going on that made you feel that way?
How are you feeling?
My logic and cognitive functions are normal.
Let's pivot a bit from eggs. Phil, what do you have to say about COVID-19 pandemic?
The real history behind the myth.
Yeah, the real story. Do you think COVID-19 is this gonna be the end of the world finally?
As of now, the answer is no, but we can't tell yet. But what we can say is that whatever happens, happens without warning. And all at once the authorities have to take over like a Siemens plant being powered from the sun. It's one party in a Titanic computer and switchboard and one tiny bit of useful trivia out of billions. And it's all handled by a totally unwritten law enforcer working in the dark, knowing everything but the question he must answer before the world begins to think it over and act. And when it acts, whether it knows the answer or not is anyone's guess. How many people are going to die before the singularity? I don't know. I hope it won't be too late, and in the meantime, they were having a wonderful time.
Well, I'm having a wonderful time talking to you now, Phil, but overall, this is not probably the most wonderful time that humanity as a whole has ever experienced, but So these two videos you've just seen, these are not AGIs, they're not human level intelligences, but they're interesting hybrid AI systems with neural nets for computer vision and for language processing, and with symbolic systems for various aspects of memory, reasoning, and goal-oriented control. And OpenCog, Hyperon, True AGI systems controlling humanoid robots like this is one sort of narrow AGI that I think can be interesting and impactful for the future, is making systems that traverse the pathway from narrow AGI toward full AGI, focusing on the application area of humanoid robotics. I mean, these systems can be very interesting both for practical applications and for getting more and more intelligence into your AI systems. The Philip K. Dick robot is basically for experimentation and entertainment. Sophia robot is a product, being launched by Hanson Robotics for a variety of purposes. We're also launching a new robot, which is like Sophia's little sister, the Grace robot. And the Grace robot resembles Sophia, but has a different AI system that's oriented particularly toward elder care. So we want to roll out the Grace robots, they're a lot like Sophia, in senior living facilities and in hospitals and old folks' homes around the world, so that the people in these elder care facilities can get the human touch of a humanoid robot that really understands them and can help them out. Now, while putting our proto-AGI systems in these robots gives an amazing interface. Actually, on the back end, most of the AI is running in the cloud, and this is where I want to give a brief mention to the SingularityNET decentralized AGI platform. So while the cloud-based portion of the AI behind these humanoid robots and behind our other OpenCog and True AGI applications, the cloud-based portion is running in this blockchain-based decentralized AI platform called SingularityNET, which you can find out about at SingularityNET.io. But this lets sort of the cloud internet-based portion of distributed AI and AGI systems operate in a decentralized way without a central controller, which gives much more robustness, anti-fragility, and security. So there's a lot of aspects here, right? There's the AGI algorithms, there's robots and software applications that deliver value to customers, and then there's this decentralized blockchain-based platform on the back end that lets all the different software processes running the cloud-based parts of the AGI system coordinate. So the crux of all this, of course, is what are the algorithms and architectures that let these AI systems think, right? And what we're doing behind these robots and our other applications is it's a new version of OpenCog called Hyperon, which is wrapped in a scalable application engine called True AGI, which is then running on SingularityNET platform. Inside Hyperon, we have a knowledge metagraph, and we then have a whole bunch of different learning algorithms, neural net, probabilistic logic, automated program learning, and others. And really, these different learning algorithms, they're all arranged around this knowledge graph called the atom space, where atoms are nodes and links and relationships. And then the True AGI application engine is what allows multiple different AI algorithms to act on the same knowledge graph in a scalable way. And the neural algorithms and symbolic algorithms working together on this shared knowledge graph, this is a huge piece of the picture. And we're touching on areas here where no one knows quite how the human brain does it, right? We know the human brain is a neural net at the implementation layer, but in a way that's sort of like saying the human brain is a bunch of molecules, right? How are the molecules organized? How are the neurons organized? Some of the neurons in the brain are organized in a way that resembles deep neural nets that are currently used for vision and language. Some of the neural nets in the human brain are organized in a quite different way, which may more resemble our current symbolic logic engines. And in our OpenCog and True AGI project, we're not trying to simulate in detail how the human brain works. We're more trying to simulate what the human brain does. And in some cases, that could mean using software that at the micro level operates a bit differently than the human brain, because computer hardware is not the same as the wetware inside the brain, right? So we're taking deep neural nets, we're taking logic engines, we're plugging them together in the OpenCog framework to operate on a common knowledge graph to control robots and software. And the nitty-gritty details here are quite different than how the wetware in the human brain works. But I think at the high level, we're doing similar cognitive things. And we're also able to deliver some powerful applications in this regard. So we've used this neural symbolic approach together with the Cisco systems to do some smart city applications and understand what's happening in street scenes to help with traffic regulation. And, this involves using neural nets to observe cars and pedestrians and so forth, and then using probabilistic reasoning and probabilistic programming to generalize, well, maybe this situation in the street is not like something we've ever seen before, but okay, we can draw an analogy to something we've seen before, and then using analogical reasoning, we can guess. There may be some danger, maybe some traffic jam here in an unprecedented situation. So say there's a political figure visiting the city. The AI system has never seen that happen before, but the AI system has seen sports events. So maybe the AI system can extrapolate from the traffic situations it saw in the context of sports events to the new traffic situations that it's seeing in the context of a political figure visiting the city. This sort of extrapolation is not done by neural nets. In our framework, it's done by probabilistic logic. And, we've worked on this on simpler robots, and we've worked with this on the more complex humanoid robots like Sophia and Philip K. Dick I've showed you. And, key aspect here, beyond just interfacing with robots and applications, and beyond just being neural symbolic, a key aspect is using the neural symbolic integration to lead to some radical computational creativity. And this could take the form of AIs inventing new things, like new medical therapies and so forth, or working with cancer biologists and COVID biologists to help understand, which therapies will work well for this people. But even a seemingly prosaic application like elder care or automatic traffic analytics requires creativity to learn new patterns to deal with new situations. And you can almost view computational creativity as a sort of cognitive chemistry or cogistry, right? You have patterns, ideas, and inspirations, perceptions in the robot's mind, in the AI's mind, and the AI needs to combine the different elements of what it's seen and thought to form new things, just as, atoms combine to form molecules combine to form compounds. So we need to make AI systems that have a neural symbolic foundation for sort of algorithmic chemistry to create new ideas to deal with unprecedented situations. And, we can get some of this cognitive chemistry magic of new concept formation in the AI's mind to work in practical applications like humanoid robotics or car traffic analytics. I think there's also a role for sort of pure education of the AI. So we're experimenting with the AGI robot preschool, where we take AI robots and put them in an environment like little children are in, and just have them experiment with building with blocks and describing what they're seeing, learning basic social interactions. And then by putting the AI minds that you're teaching in the robot preschool together with the AI minds that are helping with elder care, or that are helping with car traffic analytics, putting these all together in a shared knowledge graph running on a cloud-based framework like SingularityNET. I mean, in that way, I think we can move toward general intelligence. So we're building the AGI engine, which is OpenCog Hyperon, True AGI built on SingularityNet using multiple AI algorithms from multiple AI paradigms all integrated together. You have to teach the AGI engine by a combination of things like a robot preschool and real applications like car traffic analytics and elder care. And then once you've got, application-specific knowledge and basic childlike common sense knowledge working together in the same AGI system, then you have something that can really be rolled out as, narrow AGI systems, providing more and more general intelligence in different vertical market applications. And ultimately, all the data and learning gained by these narrow AGI systems in cross-connectedly delivering value to customers, this is what will power the transition to general intelligence. So I can't say this is the only possible route to AGI, but it's the route that makes most sense to me. I think we're on the cusp of the AGI revolution. I don't think we can get there just by scaling up deep neural nets on more and more data. I do think we can get there by hybridizing different AGI paradigms within these sort of connecting hub software frameworks like OpenCog and SingularityNet, and then by building applications addressing multiple vertical markets that operate in an integrated way and gradually learn their way toward AGI. And this is it's a big pursuit and it's a global pursuit. So I know in Russia, my team's effort on AGI is led by Alexei Potapov in our SingularityNET True AGI St. Petersburg lab. So I'd encourage everyone who wants to follow up on this more to look up what Alexei has written and contact Alexei and his team to dig in deeper, as well as look at our online materials at SingularityNET.io. Thanks.
Ben, thank you very much.